Okay, let's start. It's way too small. Okay, together we will go over 5.4 again. The later part after understanding the reference angle. Let's see how we will use them. Let's start with certain an observation. Suppose I have a unit circle. Let me make it big enough. Suppose I have a unit circle. And we have seen that from that unit circle, suppose I have a central angle, the angle in standard position, theta. Then the coordinate here must be cosine theta, sine theta. Now that's what we learned before. Now what this has to do with reference angle. What happened is the following. Suppose you consider the following rectangle. Consider the following rectangle, then you notice that this coordinate here, this coordinate here, this coordinate here, and this coordinate here, all of them have the same reference angle to what we had earlier. They have the same reference angle. This is theta also. This is theta also. And this is also theta, right? They have the same reference angle. Now, at the same time, these four coordinates are actually related in the way that, for example, this guy here is the reflection with respect to the y-axis. Okay, so this is equals to negative cosine theta sine theta, where the theta is the reference angle, right? Okay, this guy is negative cosine theta, negative sine theta. And this is cosine theta, negative sine theta. Okay, so if my angle in standard position instead is called that alpha, okay, so let's say this is alpha, okay, and the reference angle of alpha is theta, then let's say reference angle of alpha is theta, then notice that sine alpha is equal to plus or minus sine theta. Okay, in this case, because theta is in quadrant 2, then the sine alpha equals to positive sine theta. Cosine alpha is plus minus cosine theta. In all alpha, that has the same reference angle. So not only this alpha here, even if I go to this alpha or if I go to this alpha here. Okay, so we can come up with this idea in textbook that we use at West LA College. They even call this a theorem. Let theta hat be the reference angle for angle theta, then f theta equals to plus minus f theta hat for all trig functions f. It has to be trig functions, okay, with plus minus sign adjusted to the quadrant. Okay, now we have seen before that in quadrant 1 all positive, in quadrant 2 sine positive, therefore cosecant also positive, in quadrant 3 tangent is positive, and quadrant 4 we have cosine is positive. Okay, so how do we use that? Suppose for example number, let's say number 8a. What is sine 210 degrees? So we first think 210 degrees is in which quadrant? It is in quadrant 3, right? The cutoff are 90 degrees, 180 degrees, 270 degrees. So 210 is in quadrant 3, right? Okay, now in quadrant 3, sine is negative. So I put negative sine of the reference angle. Now, what is the reference angle? The reference angle is, in quadrant 3, the transformation is the angle minus 180 degrees. Okay, that's negative sine 30 degrees, which is negative 1/2. The negative comes from the fact that 210 is in quadrant 3. The 1/2 comes from the fact that sine 30 degrees is 1/2. Okay, so you look at the quadrant, that's how we know the plus minus. And then we look at the reference angle. From there, then we compute the value in terms of special angle in quadrant 1. Number 10, A. Cosine of 5 pi over 4. Now 5 pi over 4 is in quadrant 3. Again, the cutoff in radian will be 0, pi over 2, pi, 3 pi over 2. Now 5 pi over 4 is more than 1 pi but less than 1.5 pi, right? That's how we know it's in quadrant 3. Now in quadrant 3, cosine is negative. And the reference angle in quadrant 3 is that angle minus pi, minus 180 degrees. So we get pi over 4, right? Negative cosine pi over 4 is negative radical 2 over 2. Okay, so the technique basically, if the angle is in quadrant 2 or in quadrant 3 or in quadrant 4, you transform all of those into quadrant 1 first before you compute. Okay. Let's say question number 16. One more. Okay, question number 16. What is secant 135 degrees? Now that is equal to 1 over cosine 135 degrees. And then 135 degrees is in quadrant 2, right? So cosine will be negative. Okay, and the reference angle will be 180 degrees minus 135 degrees. That's 45 degrees. So this is 1 over negative 1 over radical 2. That's negative radical 2. You see? Okay. Now, what happened, Thomas, then if we have negative angle? We do another observation. What happened if we have negative angle? Let's say we have a unit circle. And we observe the following. Suppose we have angle theta here. Of course, the coordinate here is cosine theta sine theta. Okay, with the assumption it is a unit circle. Now, suppose I go negative angle instead. So the same angle, but opposite direction. Now, notice that they have the same reference angle, right? So the value of sine cosine must be the same. Okay, the value of sine cosine must be the same. Let's call this theta, and this is negative theta here. The first obvious observation is this, that we know the coordinate here has to be cosine negative theta sine negative theta. Okay, now, but the x component of these two angles should be the same. It's just reflection with respect to x-axis, right? Reflection with respect to x-axis. So the x components are the same. So cosine theta is equal to cosine negative theta. And we also know that if you reflect with respect to x-axis, the y component will become the opposite. So sine negative theta is equal to negative sine theta. Okay, so if the value here is y, then the value here must be negative y. Right? Sine negative theta is negative y, which is negative sine theta. Okay, now you can see this is pictorial proof of for B4 negative angles. Okay, cosine is an even function, sine is an odd function. Now, therefore, B4, 3 tangent of negative angle is equals to negative of tangent theta. Proof. Tangent negative theta is equal to sine negative theta over cosine negative theta that is equal to negative sine theta over cosine theta, which is negative tangent theta. Okay, that's a little informal proof there. Now then, how do we use this? Basically, if we have negative angles, make it positive first. That's one way to do it though. Okay, that's one way to do that. So suppose, for example, I work on number 10b. Number 10b, cosine of negative 11 pi over 6. There are two ways to do this. First, if I use negative angle idea first. So cosine negative equals to cosine positive. And then you observe that this angle is actually in quadrant 4. Right? Okay, it is in quadrant 4. It's almost 2 pi. More than 1.5 pi. In quadrant 4, cosine is positive. And the reference angle is 2 pi minus 11 pi over 6. That is pi over 6. So this is cosine pi over 6. That gives us radical 3 over 2. Okay, of course, we can also look at the terminal angle. The alternative way to do this problem is look at the terminal angle. Negative 11 pi over 6 is coterminal to that angle plus 2 pi. Okay, which is pi over 6. That's coterminal. Okay, so cosine negative 11 pi over 6 is equals to cosine pi over 6, which is radical 3 over 2. Okay. How about if we do number 14? 14b. Cotangent of negative 2 pi over 3. This is equal to, let me do the reciprocal first. Can I just attack that right away from cotangent, Thomas? You can, but I make it into tangent because I feel more comfortable with tangent than cotangent. Okay, and tangent negative is negative tangent. Okay, now 2 pi over 3. Then from here, I attack it this way. 2 pi over 3 is in quadrant 2. It's more than half pi, but less than pi, right? In quadrant 2, tangent is negative. So this is 1 over negative of negative tangent of the reference angle. Reference angle is pi minus the angle. Okay, negative and negative becomes positive. Tangent pi over 3 is radical 3. Okay. Now, that's the first part. Second part. The second part using calculator. Using calculator to compute trig values. Now grab your calculator, please. And later on, we go backward. If we get the trig values, find the angles. Now grab your calculator, please. I grab mine also. Unfortunately, the calculator I have on my computer is TI-84. Now, how do we use calculator to compute certain things? Let's say, for example, we take a look on number 28. Number 20A. What is cosine 88 degrees 30 minutes? Now change it to decimal first, decimal of degree. But 30 minutes is half a degree, right? So this is cosine 88.5 degrees. Is it okay? Yeah, 30 minutes divided by 60 minutes equals to, maybe I write it this way, the conversion. 30 minutes equals to what degrees? That's equals to 30 minutes times 1 degree over 60 minutes, right? That way we can cancel the minutes and cancel 30 by 60, that's 1 over 2, right? So then from there we get this is equals to 1/2 a degree, which is 0.5 degree. Does it make sense? Okay, now then you will use your calculator. Okay, now the warning is here. Make sure when you use your calculator, always be aware with what mode you're working on. Now here, my calculator, you press mode on your calculator. Here, my mode is in radian. So let me change it to degree. Okay, now then compute cosine 88.5. I don't put degree there because the mode already in degrees. Okay, so our calculator will understand this as the 88.5 is in degrees, 0.02618. 0.02618. And in my class, if you have decimal, always make it 5 decimal places, at least. At least. Now, how about number 22, number 20B? Number 20B, we have sine of 1.48. Because it has no degree sign, it must be in radian. So change the mode into radian. And then sine 1.48. 0.99588. 0.99588. Okay, no degree sign. Means it is in radian. Okay, so in the past, I once asked this question, seems to be a very silly question. Seems to be a very silly question. I asked a student, what is sine 30? Believe it or not, a lot of people say that's equals to 1/2. No, it's not. Sine 30 is not 1/2. Sine 30 degrees is 1/2. Okay, so that little degree signs there make a very big difference. Okay, you don't believe me? Well, just plug it in yourself. What is sine 30? No degree sign. Sine 30. Negative 0.98803. Okay, so make it a big warning. It's a little detail that counts though. Okay, it's that little details that counts. Now, what happens if we have a function that is not on our calculator? Let's say number 22. That is cotangent 9 degree 10 minutes. So 10 minutes is 1/6, right? 10 divided by 60. Okay, that's 1/6. In decimal, I think that is 0.16667 degrees. So this is cotangent 9.16667 degrees. Now, but we don't have cotangent on our calculator. You can see here. No, there's no cotangent. That's why we call the sine, cosine, tangent as the primary trig functions. Secant, cosecant, cotangents are just secondary. In other words, if you need to deal with the secondary trig functions, change it to one of the primary one first. Okay, then you use your calculator. This is in degrees. I need to change my mode first. Okay, that's 1/tangent 9.16667. That is 6.19703. That's 22A. How about 24B? Secant 0.26. Now, no degree sign, it must be in radian, right? Change it into one of the primary trigonometric function first. It is in radian, so make sure you change that mode to radian. Mode, change it to radian. And 1/cosine 0.26. 1.03478. Okay. Now, how about going backward? Suppose we are given that the trig values, find the angle. Okay. For now, we will deal with an acute angle. Let's say number 26. For theta in quadrant 1. Solve sine theta equals to 0.6612. Okay, only when theta in quadrant 1, you can do what I'm about to do next. Only when theta in quadrant 1. And one of the things we know is like the value on the other side has to be positive. Okay, has to be positive. Now, so theta is equals to, take a look on how I write it. I will write it. This is something I don't agree with our textbook, what our textbook's doing. They don't teach us inverse tangent, inverse sine, inverse cosine yet, but they already teach us how to use it on calculator. Okay, so if I follow the book, then you need to write it this way. Okay, now make sure they want us to write it into the nearest to angle. So my mode has to be in degree. So you see, I go back and forth degree, radian, degree, radian here. because they want in degree right now, then let's do that. Now, sine inverse is the second option of that sign. Sine inverse of 0.6612. So theta is 41.39146. Theta equals to 391. Oh, what is it? 41.39. 41.39146. Don't forget the degree sign, because you solved that in degrees, right? By the way, in case it is needed, how do we change this into DMS style? Degree, minutes, seconds. We did that before. Let's remind ourselves. This is equals to 41 degrees plus 0.39146 degrees times 60 minutes over 1 degree. Okay, so what I will do is subtract this by 41 so that we get just the decimal part, multiply by 60. That's 23.48736. 487 what? 36 minutes. And if we want to change this further into seconds, that's plus 0.48736 times 60 seconds per 1 minute. Okay, so subtract this by 23, multiply the decimal part by 60 seconds. That's 29.24 something. Let me just round it to 2 decimal places of the seconds. Okay, now because our textbook wants us to round it to the nearest decimal hundredths of a degree, then they will make it 41.39 degrees. That's in our textbook. Okay, and if we want to make it to the nearest minutes, this will be 41 degrees, 23 minutes. I try to do it even in more accurate setting. Now, the problem arises when, what if it is not sine, or not cosine, or not tangent? Let's say number 32. Cotangent theta is equal to 0.361. Now, we don't have cotangent inverse. So take a look on the reciprocal first. The reciprocal of cotangent is tangent theta, right? Then you do the reciprocal on the other side also. And just leave it like that. Don't need to make it into decimal. Okay? Now then from here, you use your calculator, compute tangent inverse of that 1 over 0.361. So let calculator does that division and apply the tangent inverse. Okay? So I will do tangent inverse of 1 over 0.361. Okay, that is 70.15042 042 degrees. Okay, that's the degrees in decimal, and usually that's all I want. Okay, but just to make our textbook happy, suppose we want to make it in DMS, degree minutes seconds, then this will be 70 degrees plus 0.15042 degrees times 60 minutes per 1 degree. Which one you talking about? Isn't it 1.2243? Do we have to change it to radian? Not the question for number 32 though. Not for number 32, not for number 26. Yeah, number 26, the question is to the nearest degrees and to the nearest 1 minute. If you look at the book. Okay, not to the radian, not to the radian. Yeah, we have to set it to degree if so. Okay, we have to set it to degree on our calculator mode. Is it what happened to my calculator? Let me check my mode. Yeah, it's already in degree. Okay, now this one here, let me continue. I subtract by 70 so that I can get the decimal parts only. And then multiply by 60. So I get that is equals to 70 degrees plus, let's see, what's that? 9.02506. 9.02506 minutes. So our textbook will end here, right? Because they just want us to do it to the nearest 1 minute. Okay, but we will go on further. This is 0.02506 minutes times 60 seconds over 1 minute. So let me grab my calculator again, subtract by 9, multiply by 60. 1.5, 1.50. That's 1.503 seconds, is it right? 348 seconds. So in DMS, that will be 70 degrees, 9 minutes, 1.53 seconds. Let's say if I round it to 2 decimal places of the seconds. It is not a custom once we make it into DMS, and we still use decimal in the seconds. It's not a custom. It's not a custom. Usually they just leave it like this. 41 degrees, 23 minutes, 29 seconds, like that, usually. Okay, in DMS. Now the thing is, once you are in astronomy, those little decimal, even in the seconds, are very, very important. Okay, that's very, very important. Just a little bit off. If let's say I round it to only 29 seconds here, then it will translate into couple hundred years or even 1,000 light years different when we talk about distance. The way we compute the distance of a certain planet, or I should say the certain star from the Earth. So this is a star, maybe it looks like a sun. Our sun is a star, right? And let's say the Earth is here. Okay, and from here we compute the angle from our sun. So this is our sun, and this is a star. Okay, then we will compute the angle. Let's say the angle here is theta 1. And then approximately half a year later, we are on the opposite of the sun. We also see the angle. Call that theta 2. Okay, now then we will use trigonometry which what we learn here. We see the distance here and the distance here, which we know. Okay, using this angle here, we will be able to find the distance here and the distance here. Okay, this is something we will learn later on. Okay, maybe not in the setting of computing distance of stars from us, but in the setting of a smaller case. Let's say this is station 1, this is station 2. This is the distance between 2 stations, and you have a satellite here. Then how high is the satellite from the ground, for example? Okay, we will learn that much later. Okay, even though in 5.7 we may be able to compute this already. Okay, now the thing is, okay, because this star is very, very far, if we go back to the context of stars, because this star is very, very far, then the angle we get here and the angle we get here will be almost 90 degrees, such that every rounding you make compromise the distance by 100 millions of years. At least 100 years, maybe millions of years of light. Okay, it's very far. Oh, by the way, this technique here is called parallax techniques. Is it parallax like this maybe, or double R? Something to do with this. Okay, I learned that in Indonesian, parallax. This is the Indonesian word. Okay, believe it or not, this technique of computing distance is something very, very natural. Very, very natural. Now it all comes from the rounding, right? Okay, it comes from rounding. I mean the discussion actually starts from. So Thomas, how do we do roundings when it comes to DMS style? I said earlier, when it comes to DMS style, we tend to use integers only. Okay, and I make you aware that when it comes to astronomical measure, we don't do rounding. It's like you go as far as possible. Okay, as far as the accuracy of your tool or your instrument allows. But do you realize the technique I showed you earlier, what we call parallax technique, is actually something being utilized by our eyes. The reason we have 2 eyes and the distance between your 2 eyes is so small, right? Okay, and if you see an item, let's say if you see your math book from certain distance, okay, if that distance is far enough, then your eyes is almost parallel, right? If it is far enough. But if you see something very, very close, then your eyes will be cross. Do you realize that? You know what I mean by cross eyes, right? Okay, why? The distance is too short. Okay, and your eyes then can give you the feeling of how far that item from you, because the angle formed by your eyes. You see? So don't you think it's kind of amazing how our eyes actually working with all the trigonometry built in there, even before you learn any trigonometry? Okay, so if you see Thomas, and Thomas' eyes are both in the middle, right? Thomas' eyes are the black part of his eyes is both of them are in the middle. Then you know Thomas is looking at something quite far. However, if his eyes, the black part of his eyes, are actually to the point of cross like this, then you know he's actually staring into something close enough. Right? You see? Amazing, huh? But this technique is actually built into our eyes, and That's what being used later on, the parallax method. Okay. Now that's the trigonometry part that goes further later on, though. But then you will be. I hope now you realize that the reason you can know the distance of an item from you is because you are looking at that item, let's say your computer or your phone or someone, because you look at that things with two eyes, not only one. You can try doing the following. You can try doing the following. Yeah, you can try doing the following. Okay, now you see, cover one of your eyes. Can you tell the distance of your other hand? With only one eye open, you cannot really tell how far that thing is. Okay, only with two eyes, then you can tell approximately how far it is. You see what I mean? Okay, now, therefore, do not drive if one of your eyes not working well. Now, I have that case I think last month. I did check on my right eye. Doctor found something, and they delayed my right eye without delaying my left eye. Oh man, for 1 hour, I have hard time to see, you know. And then because I cannot really see distance, right? A good thing I live only one block from my optometrist, so I just walk home. I left my car at her parking lot. But yeah, that's the effect. Legally, I drive with my two eyes and my glasses, right? So the police, if police got me, then I don't think they can ticket me, right? But I myself know that my left eye was working normally, but my right eye is so delayed. Okay, now that's for this question though. Let me ask you to do a couple problems before we go on, just to make sure that you get used to this. Let me ask you to do number 36. Cosecant theta equals to 11. Cosecant theta equals to 11. And just do it in degree. You don't need DMS mode. The degree in 5 decimal places. I will give you 1 minute for this. Okay, let's start. So I will first make it into 1 over sine theta equals to 11, right? So sine theta is 1 over 11. Okay, now theta therefore is sine inverse of 1 over 11. Let's see what's that. Sine inverse of 1 over 11. 5.21591. 5.21591 degrees, because it is in degree modes, right? Okay, our calculator will never write the degree sign, but therefore you need to know, oh, sine inverse something will give me angles. If it is angles, then it has to be either in radian or in degrees. Okay, but then this is not the angle, this is the angle. So when you solve for theta, it has to be either in degree, therefore you use degree sign in this case, or in radian, where you don't use the degree sign. Okay, I hope you get this, by the way. Now, we will next do a more difficult part. Oh, you know what? Let me ask you to do this further. Let me ask you to do this further. Number 38, let's say number 38D and E. Number 38D, that's cotangent of 1030.2 degrees. And part E, what is secant 1.46. 5 decimal places as always. Okay, 1 minute. Okay, cotangent is the reciprocal of tangent. So this is 1 over tangent 1030.2 degrees. I think my calculator's mode is already in degree mode. Okay, good. So 1 over, let me share this part here. 1 over tangent 1030.2. Negative 0.84507. Negative 0.84507. Now, how about secant 1.46? That is 1 over cosine 1.46, but this is in radian. So change the mode to radian. Okay, 1 over cosine 1.46 is 9.04406. 9.04406. Okay. So far we have learned to compute trig values of an angle and angle from trig values. But the one we did above, the one we did here, number 26, number 32, and number 36, they are all for acute angles. So what if we need to find theta between, for theta between 0 degrees to 360 degrees? Let's say for number 48. So we have sine theta equals to 0.8225. Let's say the theta is in degree. Okay, so I change my mode back to degree. Okay, we will use the idea of reference angle. So what we will do first is identifying sine theta is positive, so theta must be in which quadrant? It's either in quadrant 1 or in quadrant 2. Is it right? Now, take a look at the reference angle. Now, we don't know what is the angle, okay? But we know sine of that reference angle must be the positive of that number. In this case, it's already positive. So I will just copy this guy. Now, theta hat, the reference angle must be sine inverse of 0.8225. $55.33584. Now we are not done yet. We are looking for theta. We are not looking for the reference angle. Now using that reference angle, then you reverse engineer that. You know that the angle must be in quadrant 1 and in quadrant 2 to give us that sine equals to 0.8225. Okay, now then imagine in quadrant 1, if the reference angle is 55.33584, then what is the angle in quadrant 1? Now we know in quadrant 1, the reference angle is equals to the angle itself, right? That's in quadrant 1. But there are two angles between 0 to 360 degrees that give us the sine value. One of them in quadrant 1, that's what we got. How about in quadrant 2? Now in quadrant 2, the reference angle 55 degrees something is here. So what is the angle itself? Then it must be 180 degrees minus that number. Negative 124 something. Oh no, sorry, it should be positive. Positive 124.66416 degrees. Okay, so this is the first answer. This is the second answer. The danger is what happens if the sine value is negative or the trig value is negative. Let's say part D. We have cosine theta is equal to negative 0.6604. Because cosine theta is negative, then the angle must be either quadrant 2 or quadrant 3. Okay. The plan is we find the reference angle first and then adjust that to quadrant 2 to quadrant 3. Okay. So we do the reference angle first. Use the positive part of that trig values and find the reference angle cosine inverse of 0.6604. Okay, cosine inverse of 0.6604, 48,66961. That's 48.66961 degrees. That is the reference angle. But what we need is the one in quadrant 2. So I need to find this and the one in quadrant 3. Okay. So theta 2, the angle in quadrant 2 must be 180 degrees minus 48.66961 degrees. That is 131.33039 degrees. And the one in quadrant 3 is 180 degrees plus that number. That is 228.66961 degrees. Okay, so get the reference angle first, and then from there you get the angles. Okay, you get the reference angle, you see which quadrant the actual angle is supposed to be, and then adjust the actual angles. Okay, now let me ask you to try number 40C. Number 40C, tangent theta equals to negative 1.5214. And part F, I jump to part F right away. Cosecant theta equals to negative 2.3179. Okay, now remember, always first decide which quadrant they are. So in the theta here must be in quadrant 2 or quadrant 4, right? And then you deal with the reference angle. Make it positive first. Find what is theta head. And then adjust to quadrant 2 and to quadrant 4. Okay, the theta in quadrant 2, theta in quadrant 4. Likewise for the cosecant part. Okay, together with your break, this should take you around 4 or 5 minutes for both questions, plus around 10 minutes break. We come back at 9:25. No, that's way too long. 9:20. Yeah, 9:20. I did the 40C earlier. You can check your work. Now I need to change it back to quadrant 3. And quadrant 4. Okay, that's what we get. You can check your work. Our suggested homework from here is from this 5.4b. I would like you to do number 7 to number 39 should be good enough. Okay. Now in our next section, 5.5, I would like you to go to your discussion board, and I give you maybe 5 minutes to print out the a handout I post there. Let me show you first. I have a handout here. If you have your graphing paper, if you have your printer, please print this out. Yeah, if you have your printer, you please print this out. Okay, I forgot to mention it last time. And for the next half an hour, we will first time and maybe the last time in your life graph. First big topic that we will do, graphing. Y equals to sine x in detail. That's what we'll do first. Okay, so once you print it out, okay, once you print it out, I would like you to construct a table. Construct a table for value of sine. So you have the theta here, and this is the sine theta. Okay, and the theta will be for special angles. 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees, 120 degrees, 135 degrees, 150 degrees, 180 degrees, 210 degrees, 225 degrees, 240 degrees, 270 degrees, to 300 degrees, 315 degrees, 330 degrees. Okay, and feel free to use your calculator. You will see some pattern after. Okay, you will see some pattern after. I think just round it to 1 decimal place because we will graph that later on. Okay, just round it to 1 decimal place. So this will be 0, 0 0.5. I think this is for 0 0.7, 0 0.7 something. I'm sorry, 0. Yeah, 0.707. And then this will be 0.866, call that 0.9. This is 1. Okay, after you print that paper, we will round it to 1 decimal places, round it to 1. Okay, complete that. And then we will graph this. We will use that graphing paper. I customize it for us. Where the horizontal asymptote in the middle here will be our x-axis. This is our x-axis, theta, okay, and then this will be our y-axis. I'll continue on this. This is approximately 0.9, 0.7, 0.50, negative 0.5, negative 0.7, negative 0.9, negative 1, negative 0.9, negative 0.7, negative 0.5, and go back to 0. Now, once you're done with that, then notice that 0 degree, 90 degrees, 180 degrees, 207 degrees are quadrantal angle. Those are angles in x and y axis if you draw the unit circle. If you draw the unit circle, okay, so this is 0 degrees here, 90 degrees here, 180 degrees here, 270 degrees here. Okay, now the way I do this is as the following. We will start from 0 degree here. And every grid, every 1 unit you go to the right, that represents 15 degrees. Okay, so 30 degrees will be here, 45 degrees, 60 degrees, 90 degrees will be here. Okay, I mark it in yellow so that you see where's the cutoff better. Okay, again, the grid, every 1 unit you go to the right is 15 degrees. Now I will write only the special angles one. Now, please do this though. Please do this. Don't just watch me doing that. I want you to do this also. Okay. Basically, follow me doing this. And please let me know if you want me to slow down or if you have any question. This could be the first time and the last time in your life you graph a sine graph. If you don't do this, you will never do this. If you don't do this now, very likely you will never do this at all. And the thing is, your instructor in future, your Calc 1 instructor will assume you already did this before. Okay, now those are the angles in degrees. Those are the angles in degrees. Okay, now then, I space my y-axis in a way that the maximum is +1 and the minimum is -1. Now you see that from x-axis, which is y equals to 0 to y equals to 1, there are 5 units, right? It means each of them represents 0.2. Is it okay? Do you need me to slow down? -0.8, -0.8, thank you. Is it okay now? Now then, next we will plug in the coordinates. Okay, next I will plug in the coordinates. Now then, when theta equals to 0 degree, the value of the sine 0 is 0. 30 degree, the value of sine 30 degrees is 1/2. In fact, that's precisely 1/2. Sine 45 degree is 0.7. Sine 60 degree is 0.9. It's actually 0.86, but it's close to 0.9. And then sine 90 degrees is 1. Okay, so later on you see the graph of sine in from the first quadrant. If you write the angle horizontally, and it will look like this. Now go on with the second quadrant. Sine 120 degree is 0.9, and then 0.7, and then 0.5, and then 0. And then connect that. I can't really draw that way. Let me use left hand. Not good. Hey, what happened? Okay, that's pretty nice. Now then, if I go on in quadrant 3, that's negative 0.5, negative 0.7, negative 0.9, and negative 1. And go on further, negative 0.9, negative 0.7, negative 0.5, 0. Okay, this is the graph of sine in one period. This is the graph of sine in one period. Now you will see if you continue to, let's say, 390 degrees and on, you will see the graph actually just repeat the same pattern to the right, and it will repeat the same pattern to the left. Okay, now that's the graph of sine. This is y equals to sine theta. Okay, now, however, it is not accustomed to write the angle when you write, when you graph this graph of sine this way. If you graph it this way, it is not accustomed to write it in degrees. So let's change this into radian. So this is 0 radian. This is pi over 2. This is pi. 3 pi over 2. 2 pi. At least you know that one, right? At least you know that one. And if you can, try to fill in the details here. Let's say this one is pi over 4. This is pi over 6. This is pi over 3. Furthermore, this is 3 pi over 4. This is 2 pi over 3. 5 pi over 6. 7 pi over 6. 5 pi over 4. 4 pi over 3. This is 7 pi over 4, 11 pi over 6. This is 5 pi over 3. Okay, the one I wrote in gray is not that important. It will be nice if you memorize those, right? Special angles. But the one in red is important. The angles that I wrote in red are important. Now, I assume you are following me in graphing. Okay, let me know if you need more time, or actually, let me know if you are done. I want you to get this. I want you to get this graph as detailed and as precise as possible. Okay, let me give you one more minute just to make sure that everybody is done with this. Again, next I will draw the cosine graph. We start by creating the table. the values will be, if I round to 1 decimal place. Now, once you're done with this coordinate system with the table, now try to plot them and connect the dots, like what we did earlier. I will give you like approximately 3 minutes from here, 3 or 4 minutes from here. Okay, let's start. So I will get this guy, this guy, this guy, this guy, this guy. Right? Okay, so when I connect the dots, it will look like this. Yeah, that's what it looks like approximately. Okay, with, let me emphasize the quadrantal angle, the quadrantal position is here. Now let's take some time to write the angles in radian. The one in red are important. And the one in gray is less important, but good to know. no, this is not 7 pi over 6, that's right. Okay, that's what it looks like. Now we will summarize this graph into what I call 2 by 4 plane. That is something looks like this. Summary. In 2 by 4 plane, maybe I'll enlarge this a little bit so that you have a better feeling. So this is 0, maximum is 1, minimum is 1. The angle starts from 0 up to 2 pi, the middle is pi, this is pi over 2, 3 pi over 2. Now for the graph of sine, you start from the middle, you go up, go back to the middle, go down, back to the middle, and then you make it curve. Okay, this is y equals to sine x. In 2 by 4 plane, that's what it looks like. Of course, if you continue further, then it will just repeat, right? And if you go to the left, it will repeat. But that's the pattern. For cosine, let me enlarge this again. The middle is 0, maximum is 1, minimum is -1. The angle 0 to 2 pi, that's 1 period. The midpoint is pi. The midpoint of from that midpoint is pi over 2. This is 3 pi over 2. The graph of cosine starts from the top, go to the middle, going down, go back to the middle, going up. And of course, when you sketch the graph, you curve it. Okay, this is y equals to cosine theta. In both cases, sine and cosine, beside where it starts and the shape of the graph, beside those, we have the following, that the center are both 0. In other words, the graph of sine and the graph of cosine will oscillate around 0. The graph of sine theta and cosine theta, sine x or cosine x, will oscillate around 0. That's why I say the center is 0. Okay, the maximum is 1. The minimum is -1. Now, because it goes up 1, down 1 from the center, we say the amplitude is 1, which means from the center 0, you go at most 1, you go down at most 1. Okay, so the amplitude is 1. Now, for that reason, the maximum is 1, minimum is -1. The range is -1 to 1. Okay, the center, maximum, minimum, and range. The period, it finished one cycle every 2 pi. Now you need to memorize this summary. Okay, please memorize this summary. Why? Because from here on, we will go on with transformation of those graphs. Okay, we will do transformation of the graphs. Suppose, for example, we do the following. Example 1. Graph in 2x4 plane, y equals to, let's say, 3 sine x. Now we learn from our test 1, okay, if you have 3 in front of the functions, you basically stretch that vertically, you stretch the graph vertically by a factor of 3. Okay, you stretch that by a factor of 3. Now, instead of stretching the graph, I will rescale the plane instead. Okay, so I will still use the same plane. Okay, I will still use the same plane. But instead, the maximum 1, it now becomes maximum 3 and minimum -3. Okay, why? Because the amplitude now changed to 3. The center is still 0. Therefore, the maximum will be the center plus the amplitude. The minimum will be the center minus the amplitude. You see what I mean? Okay, so the range is now -3 to 3. The period is still the same, still 2 pi, which means you start from x equals to 0, you finish one period at 2 pi. This is pi over 2, 3 pi over 2. That's the graph of sine. So you start from the middle, go to the top, go back to the middle, go down, go back to the middle. So the shape of that sine graph is actually still the same. You just stretch that by a factor of 3 vertically, but instead of stretching the graph, I rescale the plane. Let me say this to you. The way I learned it in Indonesia, I'm not saying that Indonesians' way of learning is always better. No, that's not what I'm saying. But combining 2 points of view, you can see what I'm trying to say here. Suppose, for example, so this is a side note, for example, you remember the graph of y equals to absolute of x? Now, if you don't know what's the graph, drop the class. Okay, it's too late for you to say no. Okay, now I expect you to know that already, right? Okay, so the graph of absolute of x looks like this. You see what I mean? Okay, that's the graph of absolute of x. Now, absolute of x is not too hard to graph. So if I ask you, okay, can you graph y equals to absolute of x minus 3? You can say, oh, I will move the graph 3 units to the right. Is it right? Okay, that's what it's supposed to be. You move the graph 3 units to the right. Are you with me? Now, instead of saying move the graph 3 units to the right, how about we move the plane 3 units to the left? In other words, I will move this guy here to the left. 3 units. What do you think? I'm done, right? Okay, so instead of moving, let me try to let you picture this. Instead of moving, what happened? Yeah, now, instead of moving, let's say this is my plane and this is my item. Okay, now instead of moving this can to the right, what I do, I move the table to the left. You see? Okay. Don't underestimate this point of view, though. Don't underestimate this point of view, because it is actually very applicable even in your daily life, the way I live. Okay. In fact, I remember my teacher who taught me this way. She actually tell me this. She actually telling me this, and in class I usually encounter this situation. You know, sometimes like in class, let's say this is a classroom, okay, and this is the board, let's say, and Thomas is standing here writing, okay, and some students, let's say I have a student here, want to see the board, but I happen to block that person's view. What students usually say, Thomas, do you mind to move a little bit? Okay, which actually I don't mind. But if you think about it, instead of asking Thomas to move, how about this person move a little bit? Which is what some students actually do most of the time. Okay, so like if I happen to block your view, instead of you telling me to move, how about you move your point of view a little bit? Right? Okay, let's say you have a view here, a good panoramic view. Okay, you are here. Okay, you are taking picture of this panoramic view, and it happens that Thomas was standing somewhere in the middle. Then you will tell me to move. Is it right? No, that's not right. Okay, imagine if I happen to be a pole. Will you tell the pole to move? You will say you are. If that's what you do, you are crazy, right? Okay. Why all of a sudden I, as a human who has supposed to have more rights, suddenly you are the one telling me to move simply because I can move? You're supposed to be the one move. If I happen to block your view, then you move to the other side and take the picture from here. Okay. Now, of course, if I see that you're about taking that panoramic picture, then I try to be considerate. Hey, you know what, Thomas, move yourself, right? Okay. But it's actually not right. It's like kind of strange. This is just my point of view. It's like if the one blocking your view happen to be something else, you will not ask that something else to move. Right? Let's say there's a board or a trees there. Hey, you know what, trees, you block my view. You move. No, instead of you move the tree, how about you move your point of view? You see what I mean? Okay, now that's the mindset. That's the mindset I want to instill in you. So instead of you ask other people to adjust to your point of view, how about you adjust to people's tradition, learning style, right? Okay, now that actually comes to another philosophy. I have heard a lot again and again, Thomas, my learning style is this learning style. I'm a very audiovisual person. Okay, if you're a very audiovisual person, why do you graph it yourself? Don't tell me to graph. You are the one supposed to graph it because that's your learning style. If that's your learning style, you're the one adjusting to that. I mean, your learning style, but I have to adjust to that. What the heck? Well, it's not that I don't want to help, though. I mean, in fact, when I teach, I try to make it visual also. But the thing is, when I make it visual, you don't graph it. Okay. Oh, anyway, that's what my teacher said to us when she taught us about this change of frame. Okay, so instead of you move the graph, you move the frame. Okay, you move, instead of moving the graph, absolute of x looks like this. Okay, let's move the frame instead. You see? Okay. Now the thing is, imagine if you have a hard to graph curve. Moving the graph, you need to graph it again. For example, remember the graph, for example, y equals to 2 to the x plus 3 minus, let's say, minus 4. Let's say this is the coordinate system. Let's say this is the coordinate system. Okay. Now, one way to do that is actually the following. Okay, this is, I will graph 2 to the x first. 0, 1, 1, 2, negative 1, 1/2. That's what the graph look like. Okay. Now then, I will move this graph 3 units to the left and 4 units down. But that's the same to moving the frame. Instead of 3 units to the left, the frame will move 3 units. The frame, oh, why I cannot do that? The frame will move, oh, no, I cannot. No, that's not what I want. Then I will move the frame. Let me repeat doing that. This is what it looks like earlier, right? Okay. Now, instead of moving the graph 3 units to the left, I will move this graph, the frame, 3 units to the right. So I will move this guy, becomes here. And then move the horizontal frame 3 units up, 4 units up, I mean. You see? And then approximately that's what it looks like now. You see? Okay, now you can see better that the horizontal asymptote now becomes at y equals to -4. So I don't spend time regraphing the curve. I just move the frame. Okay. But the mentality, the idea behind what I teach you here is, if you have any some life philosophy to take home today, is instead of asking other people to change, how about you change your point of view? How about you change your perspective? Or instead of changing your perspective, how about you learning a new perspective from other people? Okay, that's really life though. That's really life experience. Okay, now then, let me go on. Going back to the trigonometry part, that's just an explanation. Why then we can stick with that? We can stick with that graph. Okay, so the graph of sine always look like this. The graph of cosine always look like this. Always look like this. Okay, you just change the frame later on. So let's go on. Graph, for example, graph y equals to 2 minus 3 cosine theta. This is the graph of cosine theta. being stretched 3 units and being made upside down, and then move up 2 units. Therefore, the graph will be, the center is now at 2. The amplitude is still 3 because we stretched that by a factor of 3 even though you make it upside down, right? The period is still 2 pi. But then you follow the graph of negative cosine, which means you start from the bottom instead of from the top. Because you flip that sometime, somewhere in between, right? So that's what the graph looks like. Now, what happened if I change that theta or change that x into, let's say, 2x? Graph y equals to, let's say, 4 plus 3 sine 2x. This 4 here is the center. This 3 here is the amplitude. Now this 2 here is the frequency. It will change the period. It finished one cycle in 2 pi supposedly, but because you play the movie twice faster, then you just finish it in pi. Yeah, imagine if you have a movie that runs for 2 hours, right? But you play that movie twice faster. Then you will finish that movie in 1 hour instead. The sketch of the graph will be the center is 4, right? The amplitude is 3, means you go up 3, you get 7, you go down 3, you get 1. Are you with me? The center is 4. The amplitude is 3. So the maximum will be 4 plus 3, that's 7. The minimum will be 4 minus 3 is 1. The period, originally 2 pi, divided by the coefficient of the x in the angle. Which means, even though you still start at 0, you will finish one period, instead of 2 pi, you will finish it at pi. Okay. The guy in the middle, originally pi, because you divide by 2, becomes pi over 2, right? Pi over 2 divided by 2 becomes pi over 4. 3 pi over 2 divided by 2 becomes 3 pi over 4. Okay, so if I clean that up, this will be from 0 to pi. The pi becomes divided by 2. Pi over 2 divided by 2 becomes pi over 4. 3 pi over 2 divided by 2 becomes pi over 4. But the graph is still the graph of sine. Start from the middle, go up, go back to the middle, go down, go back to the middle. That's the sketch of the graph. Can you start feeling that? I rely heavily on the fact that you already good with your transformation, your graphing. Let's do one more like this. Let's do one more like this. Suppose I have, for example, graph y equals to -3 minus 2 cosine x over 2, maybe x over 4 instead. The center is -3. The amplitude is absolute of -2, which is 2. The coefficient of cosine. Okay, but make sure you use absolute because amplitude always positive. Now from there you see the maximum is -3 plus 2, that's -1. The minimum is -3 minus 2, that's -5. The period, however, is 2 pi divided by 1/4, the coefficient of the angle. That's equals to 8 pi. So the sketch of the graph now becomes the center is -3, the maximum is -1, the minimum is -5. Oh, from here you see that the range does not equal 0, right? Which means this graph later on has no x-intercept because the range is not including 0. Now, the starting point is 0, but the period is 8 pi. So from 0 to finish one cycle, it finished at 8 pi, 0 plus 8 pi. The graph is the graph of negative cosine, means from, instead of from the top, because you make it from upside down, it becomes from the bottom. Here, and then here, and then here, and then here, and then you curve it. Okay, it's supposed to be curved. Okay, it's supposed to be curved. And to put more details, this will be 4 pi, 2 pi here, this is 6 pi. Now, what happens if I have, for example, now I do problems from the book, for example, number 20. We have y equals to 7 sine 1/2 x plus pi over 4. So you don't just start from 0 right now, you shift the graph a little bit. Okay, let me rewrite this. This is 7 sine 1/2 of x plus pi over 4. I'm sorry, pi over 2. From there, we see that the center is 0, the amplitude is 7. So the maximum is 7, the minimum is -7. How about the period? The period is 2 pi divided by the coefficient of the angle. So the period is 4 pi. However, we have something called phase shift, denoted by phi. that is negative pi over 2. Basically, we're supposed to start from 0, but you shift pi over 2 units to the left. Okay, you shift pi over 2 units to the left. So what happened to the graph? The center is 0, maximum is 7, minimum negative 7. The phase shift is negative pi over 2. So you will start at negative pi over 2. Now, one cycle after negative pi over 2 is, so think this way. This guy here will be negative pi over 2 plus the period 4 pi. That's 7 pi over 2. You see? The graph still the graph of sine though. The graph is still the graph of sine. 0, center, maximum, center, minimum, center. So the graph will look like this. That's what the graph look like. Okay, but what do we have here? What do we have here? There are two techniques to get these three numbers. The one I prefer, this is what I do myself, is this. I basically do the phase shift first, and then I add the period. Okay, now this guy here is the midpoint of these two numbers. The midpoint of those two numbers. So when I add, that's 3 pi divided by 2 is 1.5 pi. That's 3 pi over 2. And sometimes you can just do it visually, 3 pi over 2. Okay, now then this guy here is the midpoint of these two. Okay, so you do the midpoint again, you will get, when I add, I get 2 pi over 2 divided by 2 is pi over 2. This is 5 pi over 2. You do the midpoint. So I start from the phase shift plus the period, I get this. And then I do the midpoint, I get this. From these two, I get the midpoint, I get this. From these two, I get the midpoint, I get this. Okay, now that's the first technique. The second technique, we do quadrantal period. Quadrantal period is equals to the period divided by 4. In this case, 4 pi divided by 4 equals to pi. Means from the phase shift, you add pi, you get this, you add another pi, you get this, and get another pi, you get this, add another pi, you get this. Okay, so one way, the first way, the one I like is I do midpoint, 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 midpoint. Another one is you do quadrantal period. So you take the period divided by 4. Okay, and that's what you keep on adding from the phase shift. Last question, similar one. Let's say number 40. Graph y equals to -4 sine 3x minus pi minus 3. I will rewrite this first as -4 sine, factor the 3 out. This way we can see the phase shift better. Okay. Before you do the graphing, do the details first. The center is -3. The amplitude is absolute -4, which is 4. So the maximum is -3 plus 4, which is 1. The minimum is -3 minus 4, which is -7. The period is 2 pi divided by the coefficient of the angle. And the phase shift is whatever you shift to the left or to the right. Here you shift to the right 3 units. Now the graph. The center is -3. Maximum is 1, minimum -7. Phase shift pi over 3. The period is 2 pi over 3. So pi over 3 plus 2 pi over 3, this is pi. Okay, so I do midpoint, pi over 3 plus pi, that's 4 pi over 3 divided by 2, 2 pi over 3. Pi over 3 plus 2 pi over 3, that's 3 pi over 3, which is pi, divided by 2 is pi over 2. This is midpoint again, you get 5 pi over 6. The graph is upside down of sine, so I start from the middle, but I go down instead. Okay, suggested homework from here. 5.5. I would like you to actually do, just go ahead with number 5 all the way to number 39. Just do the odd ones. Okay, but every time you do the problems, make sure you answer first the center, the amplitude, maximum, minimum, period, phase shift before you go to the graph. Okay, that's for today. See you then on Tuesday.
Thank you, Professor.